Chapter 6: Thermal Expansion. Now, consider these common experiences. If you had a container with a tightly held lid, when you place it in hot water, the lid opens much more easily. If you heated a glass container completely filled with water and tightly corked, it will break. If you rubbed your hands on a flask with a capillary tube inverted in water, the level of water in the capillary drops. All these incidents are due to an increase in the volume of matter when subjected to heat. It is called thermal expansion. Expansion due to heat changes. All substances expand when heated. The lid opened easily because it expanded on heating and hence loosening the grip on the container. The glass jar cracked because the water inside expanded and thus exerted pressure on the gas jar. The liquid level dropped because the gas inside the flask expanded due to heat from the hands, thereby requiring more space. The opposite of expansion is contraction, and it occurs when substances lose heat. When the hand is withdrawn, after some time, the water in the tube rises because the gas contracted and thus took less space. Let's start with expansion in solids. Now, consider this ring and ball, both made of brass. The diameter of the ball is just slightly smaller than that of the hole in the ring. So the ball can easily pass through the hole at room temperature. Watch what happens when we heat the ball. When the ball is heated, it expands and will increase in diameter, so we expect it won't pass through the ring. And sure enough, it cannot pass through. But if you put it in cold water, it will lose the heat and contract. Let's see if it can pass through the hole this time. And yes, it does. The ball has contracted. We can also do the contraction, but using the ring. Here is another metal ball and a ring. At room temperature, the ball passes easily through the ring. Now we cool the ring in liquid nitrogen. The ball won't pass through. The cooled ring has contracted, and so the ball cannot pass through the hole. When solids are heated, they increase in all dimensions, including length. Consider this metal bar and a gauge on your screen. The two are made such that the bar fits precisely in the gauge. Now we take the bar out and heat it for some time. We try to fit it into the gauge, and we see that it doesn't fit now. And this is because the bar has expanded in all dimensions, including its length, and can no longer fit in the gauge. When we let the bar cool for some time back to its initial temperature, and we place it back in the gauge, it will fit again. And that is because cooling has caused the bar to contract back to its original length. And therefore we can conclude that solids expand on heating and contract on cooling. Next, measuring expansion in solids. Now, the amount of expansion in solids is usually so small that we need a setup that can magnify this expansion. In this setup, a small expansion of the metal bar is magnified using a long pivoted pointer. So we hit the aluminum rod and obviously we expect it to expand. And as you can see, a very small expansion is indicated by a huge jump by the pointer on the scale. Using this kind of setup, we can also be able to compare the rates of expansion of different solids when heated for the same period of time. Next, we look at the force due to expansion and contraction. As metals expand and contract, very strong forces are generated due to the heating and cooling. Consider this thick metal bar resting on a frame. Insert a cast iron pin through the hole on one end. Heat the bar for about 10 minutes. The bar expands and gets longer. Tighten the nut to hold the bar tightly as it cools. Watch what happens to the pin. As the bar cools, it contracts. It gets shorter. The increasing force on the pin eventually snaps it into two. Next, we talk about linear expansivity. Now, when the temperature of any object is increased, its length, surface area, and volume increase. Expansion along the length is called linear expansion. The expansion of a material depends on three things: the original length of the material, the temperature change, and of course the type of material. The measure of the tendency of a material to expand is called its expansivity. The three factors are related by this formula. It may look complicated, but it is not. It simply says that change in length, that is expansion, is proportional to temperature change and the initial length. A graph of expansion against temperature is a straight line, and the gradient of that line is the coefficient of expansion or expansivity of the material. This expansivity is different for different materials, and that is what makes them expand at different rates. For example, if you had a steel bar 20 meters long and you heat it from 10 to 50 degrees Celsius, it will expand by about 1 centimeter. A same-size concrete beam will expand by the same amount. But an aluminum beam will expand by double that if you heat it by the same amount. And if you look at our graph, steel and concrete are very close to each other. They expand almost equally for the same temperature change. And this is why concrete is usually reinforced with steel. Because they expand and contract at the same rates, they don't run the risk of cracking in structures. Finally, we look at the applications of expansion in solids. And we start with the bimetallic strip. Now, if two metals of different linear expansivity are riveted together, they form a bimetallic strip. For example, aluminium and copper. Aluminium expands more than copper. So if the strip is heated, aluminium will be longer than copper, forcing the bimetallic strip to bend upwards. Bimetallic strips are used, for example, in fire alarms and also in air conditioners. In this fire alarm, the bimetallic strip acts as the switch. The yellow metal expands more than the blue one. So when heated by, say, fire, the bimetallic strip bends towards the blue side and closes the circuit, causing the fire alarm to go off. When cooled, The strip regains its form and the alarm goes out. Thermal expansion and contraction is something that structural engineers and designers have to bear in mind when designing structures. If you are keen, you might have noticed some breaks or gaps on pavements and sidewalks. These are not just a matter of beauty. The joints are meant to prevent cracking by allowing for expansion of the concrete material. They are called expansion joints. Rail tracks can experience sun kinks, while a hot day can cause the steel to buckle. To avoid this, expansion joints are left between the railway lines to allow for expansion. The rails can contract and expand without damaging the tracks. A more modern method of accommodating expansion and contraction in railway lines is to taper the ends of the rail so that they overlap. Bridges made of steel and concrete are built with gaps called expansion gaps to allow for movement when the steel and concrete expands. In some cases, rollers are placed on one end of the gap to ease the movement. Rivets used to hold metal pieces together are fitted and hammered while hot. When heated, the rivet expands. It is then inserted in a hole through the two plates and hammered to create a second head. When the rivet cools down, it contracts and pulls the two plates together, holding them more tightly. Now let's talk about expansion in liquids. Now, when we are heating a liquid, we have to heat it along with its container. When the container is heated, the thermal expansion of the liquid does not correspond to that of the container. And therefore, we have to record the thermal expansion of the liquid relative to the container. We take a flat-bottomed flask having a capillary tube fixed at its mouth with the help of a cork. We fill it with a colored liquid such that the level of the liquid is at point P on the scale. We place the flask in a metal trough, pour water in the trough and heat it till it starts to boil. We observe that the level of the liquid in the capillary tube first falls to point Q. After some time, the liquid level starts rising and surpasses the initial level P up to point R. When the flask is heated, it absorbs heat and expands fast before the liquid inside. This causes the level of the liquid to drop at first. After some time, the liquid gains heat and expands more than the vessel, and hence its level in the capillary rises to R. So we can conclude that liquids expand on heating, and this expansion is greater than in solids. Like solids, different liquids expand at different rates. Take two flat-bottomed flasks containing water and alcohol such that their levels are the same. Place them in a large water bath and pour water into it. Heat the water bath until it boils. You will see that the level of alcohol rises more than that of water. So alcohol expands more than water for the same temperature rise. Next, we talk about the anomalous expansion of water. Now, whereas we've seen that substances expand on heating and contract on cooling, water shows an unusual behavior when heated between 0 and 4 degrees Celsius. At 0 degrees Celsius, all the ice has melted into liquid water. This melting is usually accompanied by contraction. However, on further heating, rather than the water expanding, it continues to contract, that is, reduces in volume, and this means its density increases. This contraction continues up to 4 degrees Celsius. Above 4 degrees Celsius, water now expands normally with increasing temperature. This unusual contraction of water with increasing temperature between 0 to 4 degrees Celsius is called the anomalous expansion of water. Because the volume is minimal at 4 degrees Celsius, it means a given mass of water has maximum density at 4 degrees Celsius. This density is slightly higher than 1 gram per cubic centimeter. We see the effects of this anomalous expansion every day. For instance, this behavior of water plays an important role in the survival of aquatic animals and plants in cold regions. During winter, as the temperature of water decreases, water at the surface of lakes, rivers and seas starts contracting. That means its volume decreases, its density increases, and thus it sinks to the bottom. This process continues until the temperature of all the water falls to 4 degrees Celsius. As the water at the surface cools to below 4 degrees Celsius, it expands instead of contracting, and hence its density decreases due to increase in volume. As a result, it becomes lighter than the rest of the water and remains at the surface of the lake. The temperature of this water goes on to decrease to 0 degrees Celsius and is finally converted to ice. As ice is a bad conductor of heat, water below the surface remains at 4 degrees Celsius. This enables the fish and other aquatic animals to remain alive in this water. It is also responsible for the formation of icebergs. These are huge masses of ice that float on water. The density of ice is 0.92 grams per cubic centimeters, which is slightly less than that of water. This makes the iceberg to float on water with only a small portion visible on the surface. The huge portion is below the water, which makes icebergs a huge risk for ships because navigators cannot see the huge mass under the water. Icebergs have been responsible for major ship accidents, including the famous Titanic. This peculiar expansion and contraction of water is also responsible for weathering of rocks in a process called freeze-thaw action. It mostly occurs high up in the mountains or cold areas where there is high precipitation. During the day, water seeps into cracks in the rocks. At night, if temperatures fall below freezing point, the water in the cracks freezes and expands, putting pressure on the rocks. At daytime, the ice thaws and contracts. Over time, the freeze and thaw cycle continues to occur, weakening the rock and eventually forces the pieces to break off. These broken rocks form what we call scree at the base of a mountain. Next, thermal expansion in gases. Now, we set up an experiment with an empty flask cocked at the mouth and connected to a beaker with water by a delivery tube. When the flask is heated, the air inside expands and moves through the tube and into the water. Bubbles of air are noticed in the water. If we allow the flask to cool down, the air inside contracts and you will see water rising up the tube to take up the space left behind by the contracting air. And so just like solids and liquids, gases expand on heating and contract on cooling. And so, What is the molecular explanation of expansion? Now, we said that all matter is made up of tiny particles that are in constant motion and attract each other. The forces of attraction in a solid are greatest and the particles are tightly packed together. The particles only vibrate and cannot move from their positions. You can imagine the forces between them as elastic springs. With increasing temperature, the particles gain more energy and vibrate faster. This energy of motion is called kinetic energy. The increased vibrations increase the distance between the particles slightly, which causes the small expansions we see in solids. Particles in liquids are loosely held by the forces of attraction and are randomly arranged. They are more mobile than in solids. The attraction forces are stronger than in gases, but not as much as in solids. In gases, the particles move randomly because there is almost no attraction forces between them. With increase in temperature, the particles gain more kinetic energy and move even faster. This increases the spaces between them even further, resulting in increased volume. Right. Now let's talk about temperature. In this topic, we have consistently talked about heat and temperature. These are related terms, but they are not the same thing. Consider these two solids. If you wanted to know how hot or cold they are, you could do that by simply touching them. But simply saying something is hot or cold is very subjective and quite relative. We need to quantify that hotness or coldness by giving it a magnitude. That degree of hotness or coldness of a substance is called its temperature. So we can put in thermometers to get their temperatures. If you tell someone that something is 60 or 20 degrees Celsius, they will clearly understand what you're saying, instead of telling them that this is hot or cold. Temperature is a basic physical quantity and its SI unit is Kelvin. But Kelvin is usually common amongst the scientific communities. In most of everyday cases, you will hear people talk about degrees Celsius or degrees centigrade. Luckily, these two scales have a relation and we can easily interconvert from one to the other. 0 Kelvin corresponds to negative 273 degrees Celsius. And so to convert temperature from Kelvin to degrees Celsius, we subtract 273. For example, 400 Kelvin is equal to 400 minus 273, which is 127 degrees Celsius. And to convert from degrees Celsius to Kelvin, we add 273. So 25 degrees Celsius is equal to 25 plus 273, that is equal to 298 Kelvin. However, it is important to note that the size of a degree on the Kelvin scale is identical to the size of a degree on the Celsius scale. For example, if the temperature of a body increases by 1 degree Celsius, then the corresponding change on the Kelvin scale is 1 Kelvin and not 272 or negative 272. Another scale you need to know for purposes of knowledge is the Fahrenheit scale. To understand the relationships, we need to first understand the reference that each scale uses. Both Celsius and Fahrenheit scales are defined using the boiling and freezing points of water. Celsius sets the freezing point of pure water at 0 and the boiling point at 100, splitting the space between into 100 parts called degrees. Fahrenheit sets the 0 as the freezing point of brine, which is a salt solution. That puts the freezing point of pure water at 32 and boiling point at 212, splitting up the space between them into 180 degrees. It means that Fahrenheit climbs 180 degrees in the same space that Celsius climbs 100 degrees. That gives 9/5. This means that Fahrenheit climbs at 9/5 the rate of Celsius temperatures. But there is also a 32 degrees discrepancy in where these two segments begin, and this too has to be accounted for. So these are the two equations for the interconversion between the two scales. And so 25 degrees Celsius will be equal to 9/5 times 25, and then we add the answer to 32. And that will give us 77 degrees Fahrenheit. And 50 degrees Fahrenheit will be equal to 50 minus 32, and then we multiply the answer by 5/9, and that will give us 10 degrees Celsius. Temperature is measured using a thermometer. This is a glass tube with a narrow inner capillary filled with a liquid. The liquid expands when heated and rises up the inner capillary. It stops rising when it is the same temperature as its surroundings. So the height of the liquid tells us the temperature of the substance. The liquid must expand or contract uniformly and by a large amount over a small range of temperature. It must be easily visible. It must not stick to the inside of the tube and should have a wide range of temperature between boiling and freezing. The most common liquids for use in thermometers are mercury and alcohol. Mercury freezes at -39 and boils at 357 degrees Celsius, while alcohol freezes at -115 degrees Celsius and boils at 78 degrees Celsius. Alcohol is therefore suitable for measurement of temperatures below -39 degrees Celsius. Next, calibration of the thermometer. Now, the calibration of a thermometer involves the marking of 2 points on the stem of the thermometer and dividing the space between them into a number of equal parts. The 2 points are called the lower fixed point and the upper fixed point. The freezing point of water at sea level is the lower fixed point or ice point, and the boiling point of pure water at sea level is the upper fixed point or the steam point. To mark the lower fixed point, the thermometer to be calibrated is placed in a funnel filled with crushed ice. The bulb of the thermometer is completely immersed in the ice. A beaker below the funnel collects the melting water. The level of the mercury in the capillary drops due to contraction. After some time, it stops contracting and the mercury meniscus remains stationary. This indicates that the ice is melting. The position of the meniscus is marked on the stem of the thermometer. That point is marked as 0 degrees Celsius and gives the lower fixed point. The upper fixed point is fixed using a double-walled vessel having 2 side tubes, one for the steam to exit and the other for the manometer, which indicates the difference in pressure between the chamber and the atmosphere. The thermometer is inserted through a cock at the top such that the bulb of the thermometer remains above the surface of the water inside. The water is boiled and the steam produced passes up through the inner chamber and descends down through the outer chamber. so the bulb is surrounded with pure steam. When the mercury meniscus remains stationary for a sufficiently long time, that point is marked 100 degrees Celsius, and this is the upper fixed point. The space between the two fixed points is then divided into 100 equal divisions. Finally, types of thermometers. Now, there are 4 main types of thermometers: clinical, maximum and minimum, the common thermometer, and the bimetallic thermometer. This is a clinical thermometer. It is mostly used by doctors and physicians to measure human body temperature. The temperature range is about 35 to 43 degrees Celsius, which is within the normal human body temperature of 37 degrees Celsius. The liquid expands and contracts along the capillary bore. The tube has a constriction just below the bulb. When the thermometer is used to take the temperature of a patient, the mercury expands, forcing its way past the constriction. When the thermometer is withdrawn, the mercury in the bulb cools and contracts, breaking the mercury thread at the constriction. The mercury beyond the constriction stays in the tube, showing the body temperature. After the thermometer has been read, the mercury is returned to the bulb by a simple flake. This is the common thermometer. In structure, it looks like a clinical thermometer. The bulb carries the liquid in the thermometer. It has a thin glass wall for effective heat transmission between the liquid inside and the body whose temperature is to be taken. The capillary bore is narrow for high degree of accuracy. The glass stem is a thick glass wall surrounding the capillary bore. It also serves as magnifying glass for easy reading of the scale. A more recent technology in the measurement of body temperature is the use of the non-contact infrared thermometer, also known as the laser thermometer. The thermometer operates by making use of thermal radiations emitted by the body whose temperature is being measured. This thermometer is useful for measuring temperatures of inaccessible areas, moving objects, very hot objects, rotating objects, or those whose temperatures are rapidly changing. It is also useful when a fast response is required. The 6 maximum and minimum thermometer is a special thermometer that is used to record the minimum and maximum temperatures reached in an area during a specified period, for example 24 hours. When it becomes hot, the alcohol in bulb A expands to push the mercury up the right side of the U-tube. The mercury therefore pushes the steel index C upwards. The steel index has a spring which holds it in position in the glass tube. When the temperature falls, the alcohol in bulb A contracts and the mercury is pulled back, rising up the left side of the U-tube. The index D is therefore pushed up. During contraction of the alcohol, index C is left behind by the falling mercury. The lower end of this index indicates the maximum temperature reached during the specified period. The minimum temperature is read from the lower end of index D. To reset the thermometer, a magnet is used to return the steel indices to the mercury surfaces. The bimetallic strip is a type of thermometer that consists of coiled bimetallic strips as shown on your screen. One end of the spiral is fixed while a pointer is attached to the other. An increase in temperature causes the spiral to curl in a clockwise direction, forcing the pointer to move over the calibrated scale. The curling is due to unequal expansion of the metals in the bimetallic strip.